so many cables I can barely walk anymore. Huh? Okay, thank you very much, Rosemary. I'm very much honored that you invited me to give a talk here. So, yeah, what I'm going to talk today about is dynamics with quadrupoles, and this was, of course, inspired by some projects by Rosemary, with Rosemary. So initially it started for me that I, at some point, had decided I wanted to do not such single stars, but binary stars, and I said, well, how difficult can it be to look at dynamics? But I started to talk with Rosemary, and there were all kinds of issues that started playing a role, or what I was interested in, namely that the stars may not just spin all in the orbit and all aligned, but they could spin in different directions and so forth, and so I started writing my own dynamics code, but of course all of this was based on Rosemary's work, where this all started. And eventually we had a project where this was about the Mercury orbit, which has a very interesting spin-orbit resonance, which means it has an internal quadrupole moment, a permanent quadrupole moment. And so this is how I got. Thank you, Daniel. Okay. I started implementing that in my code just for single quadrupoles, and eventually also for multiple quadrupoles interacting with each other. And this is what I'm going to present you something about today. But first, soon after I arrived at Monash, I started my job here. I went to visit Santa Cruz. At the time, it was, I think, considered the best astronomy department in the world. And Greg Laughlin was the department head, and he said, "Oh, Monash, isn't that where Rosemary Mardling is?" So this is what he knew Monash for, is for Rosemary Mardling being there. And he said that he just had read her most recent paper, and it was so amazing, so beautiful, and he was very happy about this, that such a work existed that he could now draw on for his own research. Okay, so back to what I want to show you about, talk about today. This is this system Arrakov, this kind of snowball, and that is where the New Horizons probe, it went past Pluto, and then after they sent it to some other weird object that I had seen tumbling in outer space at around 44 astronomical units. But it's assembled out of two smaller objects, Venu and Veyu. So this dimensions about a few 10 kilometers each of these objects. And the question is, how does such an object possibly form? And the idea is, this is a work by our own Evgeny Grishin, and so his idea, what he did and got published in Nature, is that you start off with some very wide binary system of these two asteroids at about with a semi-major axis of maybe around 1,000 kilometers initially, and they are go in an orbit, but it's inclined almost perpendicular to its orbit around the Sun. And what happens next is that there is these quasi-Lydev oscillations that make this orbit get increasingly aligned with its orbit around the Sun, but it gets extremely eccentric at the time. And it can get so eccentric that these objects will eventually smash together, and because these materials are quite soft and the energy is, or the velocities at which they will hit each other will be large enough so that they would probably sputter or at least form some kind of compound object, probably lots of crumbles flying out in space from that collision. And so that kind of doesn't work. So that's a problem. There's just too much energy available, because what these oscillations do, they take out the angular momentum, but they don't take out the energy, and so we still have all the energy. But now I set this up with my code, and I hope this is going to work. So this is now a simulation where I show these two orbits, and you will see it zooms in, and also the time scale is logarithmic. So it starts as very big time steps, and it gets increasingly smaller. And you can see then eventually they zoom in as these objects come together. And yeah, eventually at some point you can see them sort of spatially resolved. So it's also to note that these objects are not spherical, but they have some triaxial shape that we put in. And you can see them coming together and actually spinning then quite rapidly. Yes, it's very sensitive to the initial conditions. Yeah, and then eventually they collide. So there's actually something else about these kind of deformed objects. And this one doesn't work. So that when you have something that is rotating about some axis which is not the long axis and not the shortest axis, but the intermediate axis, even if this object floats in outer space, this rotation is actually not stable around that axis. If there's even a small perturbations, it does this kind of motion. So I colored these two sides differently, that it can actually flip around. So you probably didn't notice it the first time, so it doesn't just go out, but it actually flips around. It is something that when I first saw that, I found this extremely awkward. How can something suddenly spin about the entire opposite direction that it was spinning before? So I think now, did it flip yet? Yeah. Okay. Yep. Yes, you see it. Yes, now it's the other side is now on top.
Never get sick of that. Joe Monahan showed us that, demonstrating with a book.
Yes, you can also do it as a demonstration, but I have the graphics. Okay. I have these movies online if someone wants to watch them later on more. So what one has to do for this quadrupole interaction, so one can define the moment of inertia tensor by some integral and the quadrupole tensor. And with that, one can also generally define the force on your deformed object as the derivative of the potential with respect to space, and the torque as the derivative with respect to the angle, the orientation. So we define this, we have a quadrupole potential that is the interaction of a quadrupole with a gravitational monopole. And from that you get some expression of the force, and you get some expression for the torque, and then you can also show that the angular momentum conservation is that the torque is actually minus r cross f. So that works out quite nicely. It gets slightly more complicated when we have now quadrupole interactions. So we have two quadrupoles, I call them P and Q. And then the potential becomes a somewhat longer expression. So these kind of shapes here, these are tensors, the quadrupole tensors, and this is some kind of symmetric double contraction. I don't know how this is usually done, but I chose that symbol, and somewhere else there's a antisymmetric contraction with an exclamation mark. Yeah, this is the antisymmetric double contraction.
Oh, that's so
I didn't know what people are generally using, so I decided to use that sign because this was available. Yeah, but it's a tensor. We probably can do a factorial of a tensor as well. It's easy. Okay, the interesting thing is you get the two terms for the you can get the force between the two quadrupoles, and you can also compute the torques for each of these two quadrupoles, and then you can add them together, and some of these terms cancel out, and what you then find is, yes, the sum of the two torques on these two objects actually is minus r cross f, or the force between the two, and so the total angular momentum is conserved. But there is also, when you take the difference, it means that, which is not zero, so it means you can have a torque between two objects without a resulting force. Also, or it means conversely that you cannot just use this formula to get back the torques of the individual objects, but you have to do this from more fundamental calculations, from using the Hamiltonian equations to get the torques and the forces independently. So there can be basically torques between these between two quadrupoles without a net force or a contribution of that. Let's have another look at the final evolution. Why is this not running? It's supposed to be running. Here we go. So here I show again, I didn't mention this before, I have the red arrow is the angular momentum, so angular velocity, and the blue arrow is the angular momentum of these objects, and because they have different masses, the relative sizes of velocity and momentum are slightly different, and they are not aligned similar to our free-floating object because of the deformation. So angular momentum and angular velocity are not aligned. And so I think it's just nice to watch how they interact and how they get faster in interaction when they get close and then float off. Sorry. If this is too bad on the time budget.
It's okay.
But I'll show you where this goes, because we will follow this up in a little bit. So when these two objects collide, what we have to understand, how can we actually describe this collision between these two objects? Okay, now they collide. And one thing that you already see, which is quite nice, that you see that the angular velocity vectors are actually aligned in this collision. And this is how the interaction works towards these bodies, that you end up with, in many of these typical cases, with these aligned angular velocity components, which is very useful.
Do you know why?
Okay.
Why does it?
Why?
Why do they why are they nearly aligned just before collision?
Is it in your bones?
No, it's not. I don't. That's a good question. How you describe it from simple principles.
We'll work on it.
Yes. So so what I come up with is, well, okay, you can when these objects collide together, you can define, you have rotational velocities of these two objects at the surface or at the interaction point, and you have rotation rates of your objects, or the projected rotation rates, and you can also have some, will have some relative surface velocity, and using all of these, you can then compute typical impact parameters, which are one is basically the impact velocity, so how they come together. The next one is shear velocity, so they can have a shearing motion as well. Then there is, when they come together, they can also rotate, so there will be a twisting motion on that. And finally, they can also have a rolling motion, that they roll past each other a little bit. So this is the last component that comes in. There's 6 different parameters that you actually need to describe this collision. I was trying to find out what people usually do when they do collisions. I called up the people at Accident Research, how they describe car collisions, but they did not do anything like this at all. And it's much more simpler, but in principle, all of these things should play a role when two cars collide as well, because when you hit them very hard, they could fly off. And this is how I would thought you would do it when you did collisions of objects that can rotate from general principles, that you have these different things that play a role when you have accidents. But in this case, we have only spatial accidents or collisions. Okay, so from this last point that we see at the end of the previous slide, Uri Malamud did some simulations of what happens. Why is this at the? This is interesting, because my slide here is different from that. Okay. Maybe it didn't go to the end. So we had the initial collision, and eventually these objects. Let's see if I go back and. Here we go. I can go previous and forward here manually. It's always very slow. Okay. Here you see, okay, there was the first interaction. And what is quite interesting is that when you have these interactions, for example, the first interaction, it hits it and carves out some part of the surface, and these craters that you get here look almost exactly like the craters that we have seen in Arrokoth. And so they may not be from some other impacts, but it could actually be that it has just formed from carving out from this interaction. So what we, 2 more slides, Daniel. So when we did all of these simulations, we did a big Monte Carlo simulation, and it turns out that there's some of these central collisions that give you sputter, but there's also a lot of these collisions that can occur where both of the spins are aligned and the things comes together very softly, and where all of this orbital energy that used to be there is actually transformed into rotational energy of these objects. And you can roughly estimate from order of magnitude that, yes, the maximum spin of these objects is roughly comparable to their kinetic energy that they would have had coming in from infinity. There's also other cases where you, instead of having the collisions, you end up with many systems where you just can form some captured very close binary asteroids. So this is also a way to form these kind of systems. All of these simulations were done with initially very little rotation, but if you actually give them already initially some spin, then this tidal interaction can make these systems very rapidly to evaporate again. So there's also something of that kind that will happen. So in summary, so the gravitational interaction of permanent quadrupole moments can lead to interactions that avoid these kind of hard collisions that usually would sputter asteroids when they come together. But instead, you can get aligned rotation with rates that are comparable with the mean angular velocities of the orbit. And therefore, you can make these objects such as Arrokoth or capture asteroids into very close circular orbits.